Now we'll see one example. So 16-bit representation is given, and the layout is also given. This is sign bit, and this is exponent. This is mantissa. Okay. Now x is 63 exponent. That means, so this exponent is biased and the bias is 63. That means when you write 0 here, then 63 will be subtracted from that. So we know that, right? Like x is 127. Now 2.5 is to be represented. That's a question. The data is 2.5. So there are three questions. One is 1.m representation, second one 0.1m representation where one is implicit, 0.1m representation where one is explicit. We will see one by one. Let us begin with 1.m representation. So to represent 2.5 in this set of 16 bits, what we have to do? I will tell you. First, blindly convert this 2.5 into binary. So you know the model, right? So take this integer component and convert it into binary. It is 1 0 point. So 5 0, this is 0.5, correct? So what is the, how to convert 0.5 to binary? Already I told you, right? So you get 1 here. Did you remember? So 0.5 into 2, 1.0. Then 1 we have to write here. Then the remaining portion is 0. Then we have to multiply 0 with 2. 0 into 2, 0.0. Then this 0 will come here. This 0 will be again multiplied with 2. So whenever you get 0, you stop it, because after that always you get zeros only. So in that way we can represent 2.5. This is 2, this is 5. Already I explained you how to represent 0.5 in binary. Any fraction like 0.75, 0.375, how to convert, already I told you. Follow that procedure. Once you get it, this 10.1, but actually you know the model, right? Here we have to write, we have implicit dot like this mantissa is like this, point, then remaining thing, correct? So here what I want to tell you is, in your mantissa there is no integer part, only you have fraction part. So that's why what I do is I just do right shift. So this 10.1 can be written as 0.101. Recall, when you have 1.5, if you want to make it 0.15, then we have to multiply with what? 10, correct? In the same way, if you have 10.1, then if you want to make it 1.01, that means if you want to shift that point to left side to make 1.01, in base 2 we have to multiply with 2. You can check it out. If you multiply this 101 with 2, then you will be getting again 2.5, no doubt. Check it out. Example, what is 1.01? This is binary version, be remember. So 1.01, this is nothing but 1 means what is the weightage? 2 power 0, 2 power minus 1, 2 power minus 2. Let us simplify. This is 1 plus 2 power minus 2. That means 0.25 into 1.25. So it is 1.25. So to represent 2.5, we used 10.1, perfect. But whenever I shift this point left side, I got 1.01. But 1.01 is only 1.25. So 1.5 into 2 is 2.5. That's why whenever you left shift point, then we have to multiply with 2. Similarly, when you left shift to this point, when you made 0.15, to have equivalent value, we have to multiply with 10. Same way, right? So finally what I realized is, to shift this point to these two positions, which is what I want, to make it 0.101, that means to get the same value, then we have to do 0.101 into 2 squared, right? So this one equivalent to this one. Finally our 2.5 is nothing but in this mantissa into base power exponent form. It is 0.101 into 2 squared. Okay, slowly we will try to tune this base also, sorry, exponent also. So this part is done, mantissa part, correct? Now unfortunately, actually I want 1.m, right, not 0 point version. To have 1 point version, now same thing, what we do is I use 1 2 and I multiply this 0.101 with 2, then this point will be right shifted, then I get 1.01 into 2 power 1. So this is what exactly I want. You see 1.m, right? So that's why I got into I changed this to 1.m format, 1.m into 2 to the power of 1, right? So this 1, but you know the format, right? Remember one thing, whenever it is x is 63 exponent, generally the structure like this, minus 1 whole power s into 1.m into base power exponent. This will be given in the question sometimes, okay? How to understand this pattern? That means what is the conversion formula they will mention. So it is e minus 63, x is 63. So you tell me, in the place of e minus 63, now here you have 1. That means what? If you write here 1, then that is not actual 1, right? To represent, to have 1, then we have to write 64. Because 64 minus 63 is 1, correct? So that's why what we have to do is we have to represent, see, 64. When you represent 64 here, that is equivalent to 1, because we are going to subtract 63 from that. So that's why finally, so it is nothing but 64. I will explain everything. This is finally 1.m into 2 power 64 minus 63. So I got exponent, right? And I got mantissa, this one. Blindly fill them. So mantissa what I got is 0, 1, and remaining things I can fill with zeros, right? 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Next, exponent part, 64, right? So 64 can be represented like 1, 0, 0, 0, 0, 0, 0. Let us check. We have 1, 2, 3, 4, 5, 6, 7 bits. 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6. It is 64. When you write here 64, then 63 will be removed, you get 1. So finally, this will be the answer. But what about sign bit? 0, because we have positive number 2.5. So now if you have any doubt about why it is correct, again you convert that into answer. That means value. Minus 1 whole power 0. So there is no doubt for you about this positive or negative thing. The only thing value, right? So value is what? Mantissa into, right, 1.m. This is m. I am writing m. 1.010000 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Base 2. Mantissa into base 2 power exponent minus 63. What is exponent value? 64. We know that. So now let us simplify. It will be 1.01 base 2 into 2 power 61. 64 minus 63, 1. So finally it becomes 1.01 base 2. Let us convert it into decimal so that I can understand the value. So I am converting into decimal. First of all, let me convert this to decimal. Weightages are important. 2 power 0, 2 power minus 1, 2 power minus 2. 2 power 0, 1. 1 into 1, 1 plus 2 power minus 1 into 0, 0 plus 2 power minus 2 into 1, 1 by 4. You got 1.25. Sir, but we used to have 2.5, right? It's not done. We have 2 here. 2 power 1, 2. 1.25 into 2, 2.5. So finally, 2.5 is represented like this. Okay. Now what we do is, rather than solving the same problem for question 2 and question 3, for question 2 and question 3, we take another number. Let us take 7.5 and minus 7.5. How to represent it? We will see. The first step, forget about minus. In the place of sign bit, if I write 1, that will become minus, right? So I am erasing this part first. Okay. So 7.5. Blindly convert 7.5 to binary. So we can do, integer part separately, decimal point separately. Okay. Now let us take 7. 7 is nothing but 111.5. 5 is nothing but first bit 1. Correct. Sir, I want a difficult value. Then you take 7.75. So how to represent 7.75? We'll see. I have represented 7. Now 7.75 is nothing but 7 plus 0.75. Now we have to represent 0.75 in the binary. Here we have to represent 0.75 in the binary. I will tell you the technique. 0.75 into 2 is 1.5, right? Then 1 will be here. 0.5 will be here. 0.5 into 2, 1. 0.0. 1 will be here. 0 will be here. 0.0 into 2, 0. Stop it. So here itself you can start because any number of zeros we can write here, right? So this is about conversion. We have now finally 7 point, this is 7.75. Okay, you can cross check if you want to know what is the value of this one. Give the weightages 2 square, 2 power 1, 2 power 0, 2 power minus 1, 2 power minus 2. That is what the idea, right? So this is the way we can convert into decimal back. Right. Now you have 111.11. How to represent it in dash form? 1.m representation. Already we have done it, right? So you can do it, not a problem. Let me take 0.1 m representation. To have 0.1 m representation, I should not have any integer part, right? This part should be shifted. Okay. So let us do this 0.1 m representation. So for that point, I am moving like this 1, 2, 3. If I move like that, then I get 0 followed by 0.11111 into, since I moved this point left side, right, left side 3 times, then we have to write here 2 cube, both are equivalent. Once it is done, now see 0.1 m, right? First, in the first question, 1 is implicit. 1 is implicit means what? So in this 0.1 m format, we are not storing the first one, right? So the first bit we are not storing, then only see 0.1 m. This is actual mantissa we are going to represent, and this one is default. Okay, so this is nothing but about normalization, so that always you will have unique representation for 7.75 if you do like this, correct? Now in this model, so 1 is implicit, then remaining thing is 4 ones. In the mantissa part you write now only that 4 ones. Fine. What about remaining 4 zeros? Done, mantissa part. What about this one, base power exponent? 3 is nothing but 64 minus dash is 3. Definitely we have to represent here 66 to be represented. So let us write 66 in binary. We know that, right? So 2 power 0, that means 1, 2, 4, 8, 16, 32, 64 are the bits. To have 66, 1 here, 64 plus 2 here, remaining things are zeros. So this is 1, 2, 3, 4, 5, 6, 7. Yeah, exponent is done, but it is negative number. That's why here minus, that means 1. So this binary pattern represents, you know, 7.75 in 0.1 m representation, where 1 is implicit. Understand? So instead of 5 ones, only we have to write 4 ones. Now the last one, 0.1 m representation, where 1 is explicit. That means 1 also we have to, you know, represent here. That means what we got, did you remember, we got 1, 2, 3, 4, 5, correct, into 2 power 66 minus 63. So we have to represent everything because this 1 also explicit. So it is like now, so 0.1 m, this entire thing is actually mantissa. Okay, so here we have to represent everything. Apart from mantissa, we have to represent 1 also. You can say like this. So this one is this one. We should explicitly store it. Then remaining 4 bits. 1, 2, 3, 4. Followed by 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. Everything is same. That is the only difference between these two. Otherwise everything okay. But in IEEE 754, we have only 1.m model. We cannot represent using 0.1 m and 0.1 m where 1 is explicit. That kind of things are not there. Okay. So in old systems, then we used to have these models, but IEEE standard says that it's a 1.m representation. Okay, of course there is no big difference, right? Not a problem. So this is about given a value, how to represent using, you know, 1.m representation and 0.1 representation. Okay. Now what we do is we take a pattern and we try to convert it into value. Okay. Given a pattern, what is the actual value which it represents? We will see that.